Hi everyone, we're going to talk about Beers Law in this video. You might hear it called the Beer-Lambert Law, but I usually just call it Beers Law. This diagram of a very simple spectrophotometer I think will be helpful as we talk about Beers Law. Here it is. Beers Law says that absorbance A is equal to epsilon times B times C. So I already defined A as absorbance, and if you're in lab, you probably made a lot of calibration curves where you've plotted absorbance against concentration. So that's what the C is here, concentration, and you got a straight line. Now, what about epsilon and B? Well, I think in the previous video, we sort of alluded to B. B can be added here on our diagram. This is B. B is the path length that the light travels through our sample. And isn't that interesting to notice that if you increase the path length, you increase absorbance. Hi everyone, I wanted to interrupt the video and give you a visual on path length. I'm holding a cuvette in my hand and you can see, I hope, that the path length is about a centimeter. Compare that to the burner head in a flame AA, which you might have used in lab. Here's the path length. The path length on this thing is about 10 centimeters. So again, if you increase the path length, you're increasing the absorbance. Now, let me ask you this. What if you were running very concentrated samples and you didn't feel like diluting? Couldn't you turn your burner head such that this path length that was 10 centimeters, what if you turned it this way? And now, if the radiation from your lamp is shining in this direction, your path length is less than a centimeter. So again, if you decrease the path length, you're going to decrease the absorbance, and maybe now you don't have to dilute your samples. That's a trick that some people play, but I've never played it. I'll take you back to the video now. And that leaves epsilon. In the old days, epsilon was called the extinction coefficient. The extinction coefficient, but more commonly these days, it's called the molar absorptivity. The molar absorptivity. And this is a quantity that is solute dependent. It varies from analyte to analyte. It just describes the ability of your molecule, let's say, to absorb radiation. What functional groups does it have? What is its three-dimensional shape? What is its cross-sectional area? How good is it at capturing photons? So again, this quantity depends on your solute, but notice, if it increases, so does absorbance. Let's make a note that both absorbance and the extinction coefficient or molar absorptivity depend on wavelength. So if we were to measure the absorbance at different wavelengths, that would give us an absorbance spectrum. An absorbance spectrum is simply a plot of A, absorbance versus wavelength, and maybe for a molecule dissolved in some solvent, it might look like that. And I want to point out to you that the place where we have the maximum absorbance, the corresponding wavelength is called the lambda max. That's the wavelength where absorbance is the maximum. And you may remember that in lab, the lambda max for that molybdenum blue complex that you made was 690 nanometers. That's why you made your measurements there, because that's where this complex had its highest absorbance. And I actually found an example absorbance spectrum for that molybdenum blue. Here it is. Don't pay any attention to the red or black lines, only pay attention to this blue line. Didn't you use tin 2 chloride or stannous chloride to prepare your molybdenum blue complex? This is the absorbance spectrum of that molybdenum blue, and isn't the lambda max very close to 690 nanometers? And I just want to remind you of something that you probably learned a long time ago. Why did that substance, that complex, appear blue? Well, look at the intensity of the absorbance from about 400, to maybe 500 nanometers. It's pretty low, isn't it? There isn't that much absorbance, so molybdenum blue looks blue, but look what happens at these higher wavelengths. That's where we start seeing a lot more absorbance, and because there is high absorbance at these wavelengths, and molybdenum blue absorbs the red, the orange, the yellow, and the green, it doesn't appear those colors. It appears the color blue because it does not absorb there. So that's a very brief introduction to Beers Law. I think in the next video, I'll tell you about some limitations of Beers Law.